Okay, guys, today we're going to learn about the composition of pure substances. Our learning objective is to explain the quantitative and the numerical relationship between the element's composition by mass and what's called the empirical formula of a substance. And these are about pure substances. Okay, so some essential knowledge we'll be learning is some pure substances are composed of individual molecules, but others consist of atoms or ions that are held together in fixed proportions. We're going to learn the law of definite proportions is the ratio of masses in any pure sample of a compound is always the same. So the mass percents are always the same as long as it's a pure substance. Lastly, the chemical formula that lists the lowest whole number ratio of atoms of the elements in the compound is called the empirical formula. So that's what we're going to be studying today. So, what are pure substances? Well, we have elements, compounds, and molecules. We also have ionic compounds. An element is anything you see on the periodic table. For example, carbon. Another example, lithium. Another example, oxygen. Even though it has that too, as we learned in basic chemistry, that's a diatomic, but it's still an element because there's not two different types of elements. It's only one type of element. Okay? Then we have our compounds and molecules. When we have compounds and molecules, we're talking about something that has more than one type of atom. So you have carbon with oxygen, or N with H, etc., etc. Now, when we're talking about molecule, we use that word molecule when we're talking about something that's covalently bonded. Remember, covalently means they share their electrons. So they're connected by bonds. When you have a molecule that's covalently bonded, then when you see its formula, CO2, that's literally the amount of C's and oxygens there are. So you have one C and two O's, and that floats around as a molecule. Over here you have one N and three H's, and that floats around as a molecule. As a molecule. So we have molecules, they're covalently bonded, and what the formula says is exactly how many atoms are in that item. On the other hand, we can have a compound, specifically ionic compounds. These are not covalently bonded. And in this case, even though it says one Na and one Cl, that doesn't mean there's actually one Na and one Cl. That's just the ratio they appear in. Ionic compounds really exist as lattice structures, where there's a bunch of atoms together in certain ratios. And that ratio in this case is 1 Na to 1 Cl. 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 And typically the positives and the positive and negatives, they arrange themselves to where positive and negatives attract. This is what's called a lattice structure. So in reality, there's a whole lot more than one Na there, but the ratio, the lowest ratio, it's a 1-to-1 ratio. So we show that in its chemical structure. So that's what a difference between the ionic compound and the molecule is. But they're always a specific ratio. 1 C to 2 O's, literally that amount. 1 Na to 1 Cl, not literally that amount. But that's the ratio. Okay. Now, the law of definite proportion says that in any pure substance, whether that's an ionic compound or a mixture, the ratio of the masses of that element will always be the same. So, for example, for NaCl, that 1-to-1 ratio that we have here, The mass of NNA is 22.99. The mass of ACl is 35.45 for a total molar mass of 58.44. If we were to take that percent composition, this part, 22.99, divide by the whole mass, we would find that this is 39.34% Na. I do the same for Cl. Cl's mass of just the Cl divided by the 58.44, which is the whole molecule of the whole compound, multiplied by 100 in this case, it's 60.66% chlorine. So this ratio of Na being 39.34% and Cl being 60.66% will be present in every single pure NaCl. If there's no contaminations, that will be the percentage. Okay, so if we want to find the percent composition by mass, which is what I just did, which is very important to being able to tell what it is most of the time, what we do is what we just saw. Mg, Cl. Here there's 1 Mg for every 2 Cls. That 1 Mg is 24.31. The Cl is 35.45. That's its mass. You can find that on the periodic table. When we add these up, we get 95.2. So what we basically do is we take this 24.31 and divide by the molar mass times 100. We take this, divide by the molar mass times 100, and we get its percent compositions. So the percent composition of magnesium is 25.53% by mass, and the chlorine is 74.46% chlorine by mass. And that is my percent composition of MgCl, which will never change. If Mg is anything but 25.53%, that means there's contamination present. One of the big things about this percent composition thing is we're trying to identify, in real life, we're trying to identify what something is and if it's contaminated. And that's what you're going to see a focus here. All right. So as you can see in the next question, this can be used to help us detect contamination. If we analyze our magnesium chloride and find that 70% chlorine, it can't be pure because pure chlorine has 74%. So if we're asked which is the most likely contaminant, CaCl2 or LiCl, well, we can figure this out one of two ways. First of all, we can just think about it. Okay? If calcium, which has a higher mass, it has a mass of 40, then Li has a mass of 6. Well, if Ca's mass is higher, then Cl must be lower percentage-wise because the percentages are always going to add up to be 100%. If Li's percentage is lower, then Cl's percentage must be higher. Well, the Cl of pure magnesium chloride is 74%. Our contaminated one is 70%. So the chlorine's lower in our contamination, pointing me to CaCl2 as the contaminant because the Cl is lower percentage in this one. Now, let's do it numerically and prove it. Let's calculate the percent composition of CaCl versus LiCl. So Ca's mass is 40.08. Cl has 2 of them and 35.45 each for a grand total of 40.08 up here, 70.09 down there. Molar mass is 110. Now this time I'm only going to calculate the chlorine because that's all I'm really interested in. So 70.09 divided by the 110.17 times 100 gives me a percentage of chlorine of 63.6. If I do the same for lithium, 6.94 over here, we've got just one chlorine, so 35.45 for a grand total of 42.39 for the molar mass. If I take the chlorine and divide by that molar mass times 100, I get 83.64%. So, whatever contaminant was there caused the percentage to go from 74 to 70. It lowered the percentage. If you think about this, like with test grades and stuff, the only way you're going to lower your percentage is if you have a lower grade. So in this case, CaCl has the lower percentage of chlorine, so it must be what's contaminating this. Okay. Now, once we get past the percent composition, which we use a lot, then we can start saying, well, let's talk about empirical formulas. Since the law of definite proportions tells us that for the lowest ratio of masses that make up a pure substance, that percentage will be the same. Well, the empirical formula for this, we can get the lowest proportion. We can simplify this to get the empirical formula. Okay. So, if I simplify this to get the empirical formula, 2 and 2 will simplify to 1 and 1. And we don't write the 1s. 6, 12, and 6 can all be divided by 6 to get 1 C, 2 H's, and 1 O. Okay. MgCl, well, it can't be divided by anything because you can't divide anything by 1 and get a whole number. So it's already in its simplest form. And the same here with H2O. Oxygen has a 1. We can't simplify 1, so it's already in simplest form. Note, ionic formulas are always going to be in the lowest ratios already. Because up here, we already said that the lattice structure of an ionic compound, there's a whole lot of these atoms in reality, but we write the formula as the lowest ratio, so it's already going to be in the lowest ratio. So an empirical formula is a formula that lists the whole number ratios of an element in a compound. The lowest whole number ratios, so the simplified form. All right. So what's important about an empirical formula? Well, what's important about the empirical formula is it's a middle step into figuring out what something really is when you're dealing with lab. So when we get lab data, it's important that we're able to calculate to find an empirical formula. So the point of finding an empirical formula, calculating it, is to be able to find the empirical formula, basically what it is, from mass data acquired in lab. So in real life, we're in a lab, we're getting data, and not one thing is going to stand up and shout, I'm CHO, I'm whatever. We're going to get masses from this. And from these masses, we're going to find what it is. So our steps are right here. We convert the mass of each element to moles. We divide all moles by the smallest number of moles. And then, if the numbers don't come out to be whole numbers, we're going to multiply by the factor that makes them whole numbers. We're going to find a shorter way of remembering this in a moment, but first let's do some problems. So, in the first example here, we've got lab data that gives us grams. We've got 0.0134 grams of iron. We've got 0.00769 grams of sulfur. And we've got 0.0115 grams of oxygen. Our first step is to change these to moles, and we do that like we did all last year by using dimensional analysis. The molar mass of Fe is 55.85 grams per mole of Fe. The molar mass of sulfur is 32.06 grams per mole of sulfur. The molar mass of oxygen is 16.00 grams of oxygen per mole. And we find the moles in this case. And the moles for the first one is 0.000240 moles. The next one is 0.000240 moles. The next one is 0.000719 moles. Now, I've never seen a formula, because this is the ratio here, but I've never seen a formula of Fe 0.00. That doesn't happen. So we need to get these to whole numbers. The easiest way to get them to whole numbers is dividing by the lowest one. If we divide by the lowest one, then that becomes a 1 and everything's higher. So of these three, 0.000240 is the lowest moles we got. So we're going to divide all by that number. What happens now is that this one is now 1, this one's now 1, and this one is now 3. Now we're not too worried about decimal places on this. If it's really close to 1 or really close to 2 or really close to 3, because that's what we're trying to get to is a whole number, then we just go ahead and write that number. Now if it's like 0.25 or 0.2, that's a different story. And we'll deal with that on another page. All right. So now that we've got the ratio, remember, empirical formulas is the lowest ratio possible of whole numbers, and that the percent composition is always the same for a pure substance, so this ratio is going to apply to all. That means that my Fe must be only one. My S be only one of them. Oxygen must be 3 of them. So my empirical formula set of masses is FeSO3. That was a nice one. So we'll go down to the next one. Now this one is a little different. If we have percentages, the easiest way to deal with percentages to get them to grams is to pretend assume we have 100 grams of the substance. And we can do that because these ratios are the same whether we have 5 grams, 10 grams, 20 grams. The percentages are the same for a pure substance. So if we say we have 100 grams and 50% is 50, 25% is 20, or in this case, 25.93% is 25.9 grams. Easy way to get to grams. Now, for this particular one, it says a common oxide of nitrogen contains 25.93% N. When it says an oxide of nitrogen, that just means there's oxygen attached to it. And if we have 100 grams or 100%, then if we have nitrogen at this, the rest of it would be 100 minus 25. The rest of it would be the oxygen. So in this case, the rest of this would be 74.07. So basically these percentages are always going to add up to be 100. And then we change it to grams. Then we do the same thing as we did before. Hold on. Okay. So we have the mass of nitrogen is 14 grams of nitrogen. For oxygen, it's 1600 grams of mole. When we divide those out, we get 1.8 moles of hydrogen, and we get 4.63. I said 6, sorry, of oxygen. Now divide by the lowest. The lowest of these is 1.85. In this case, we get 1. But in this case, we get 2.5. That's not close enough to round to a whole number. So basically, if you get a 0.5, in order to get this to a whole number, we're going to multiply by 2. And if we multiply 2, we're going to have to multiply the other 2. Because the ratio has to be the same. So if we double one, we double both. That gets this to be 2. Now we have N2O5. N was 2. N2O was 5. We got N2O5. Okay? Now we got another one. Okay. In this one, we have a composition that has 35.00% nitrogen, which we changed to grams. We've got 50.96%, which we grams of oxygen. And the rest, so what's the rest? Well, we subtract those two from 100, and the rest is 5.0, and that happens to hydrogen. So 14.01 grams of nitrogen, mole of nitrogen, mass, 16.00 grams of oxygen, and 1.01 grams of hydrogen is 1 mole of hydrogen. For this, we get 0 moles nitrogen. For this, 5 moles, and for this, we get 9 moles of hydrogen. Divide by the smallest, 2O. And this one comes in all the rest of them 1. In this case, 1, 1.5, and 2. So once again, we have a 5. So we're going to multiply everything by 2 to get rid of 5 and make it a whole number. So we have 2 of these, 3 of these O's. We've got 4 of these H's. All right. Now, the way I remembered it from years to years is by thinking about this. Percent to mass, mass to mole. By small, multiply to whole. It makes a little rhyme. Remember. Percent to mass, mass to mole. Divide by small, multiply to whole. Now, the multiply to whole, that's what I was doing a while ago when I had 0.5 by 2. You might not end up with 0.5. You might end up with like 0.2 or 0.25 or 5 or like 0.33, 0.67. In that case, it kind of lets you know bye-bye. So that's it. You can practice your, and we'll see you on the next video.